power transformer, not a perpetual motion of free energy machine. This device does not violate any fundamental laws of physics, nor does it utilize any new technologies or processes. It does utilize processes that are well established and in widespread use in modern industry. It combines these processes in a unique, more harmonious manner, thereby securing more electrical power transformation for the same amount of power input. Now listen as the inventor runs the machine and explains what is taking place.
This is just a standard SCR speed control for the DC drive motor, standard drive motor. It's just to spin this thing at the speed. Used for starting in this really crude implementation here. The big thing there, that's the actual power converter. You can see it's been custom modified in the engine extended. It has two sets of slip rings and a commutator and various other things on it. And then the light bulb, is just a light bulb socket. After oscilloscope to display your frequency. And digital voltmeter displays the output voltage, generated output voltage. And this unit here with all transformers is just the power supply. And the reason you use all the transformers is just to facilitate getting a certain voltage and not be hooking directly up to the power of the wall. It acts as an isolation transformer. It's not smart to go right into 20 amps of power. And this control box here simply turns that on and off. Okay, there it goes. Not quite so good. It's really too fast, and there it goes that way. There you go. You almost got it. There it is. Now we disengage the SDR drive, and this motor is now completely stopped. So it's running all by itself, and you can see the voltage went up to almost 150 volts. Okay? This is how it works. Now that this unit itself is running completely separate. This is the unit being used here. And the difference is from 112 volts to 150 volts. That's your advantage. You have almost a 50 volt advantage. It gets coming in like 38 volts out. And you obviously can tell the different brightness of the volt is. So that's the two. The initial mode you had 120 volts was just run this as a normal generator. And then we switched over to pull this belt off so I'm not using this drive motor anymore. This just spins up to speed and then we can run it. It's a method of starting the whole thing. So your advantage ends up being, in this case, it was 38 volts. Which it just depends how much current you're flowing, depends how many watts that is. You got a 60 watt bulb that's going like, I don't know, 15 watts or 17 watts. So if you have a 120 watt bulb, it ends up being 38 watts. And so on. So the more current you draw, the more advantage you get. Power is run as a normal generator. Pull the belt up. And this is the difference. You can obviously see the difference in the light bulb going from a normal generator unit to this kind of process of increasing your output power. The advantage here obviously is the fact that we're utilizing a normal motor generator type design. So you can modify off-the-shelf equipment. And now if you were to actually measure the input and output power, you'd be able to see that this unit's producing more power than it's taking in. And this is a very simple, crude implementation that really needs to be developed. But the extra output power is just obvious. You went from 112 to 150 volts. And all it needs to be is developed a little bit into a marketable price to replace any kind of a generator setup. But it runs off of conventional equipment we can modify any kind of existing generator setup. And if you design something like this, you'd initially design the unit to run at a lot lower initial voltage so that when it actually stepped up the voltage when you turn the process on, it'd be at 120 volts instead of being at a too high voltage like we are now at 150. So your initial voltage would be much lower to make it a more practical process. You see right now the unit's tied to, it's tied right to 60 hertz or 3600 RPM, right to the line frequency. So the unit's running exactly 3600 RPM. But the same speed was running out with a DC drive motor, but only producing 112 volts. I guess the crucial thing to point out here is that the current draw on the motor hasn't gone up at all. In one case, we're using a DC drive motor. We're putting in the exact same amount of power we're putting in now into the unit separately, but we're getting out a lot more voltage. So your input power doesn't change at all, but your output power goes up substantially. And that's the real key to the unit. The input motor doesn't know the difference. It doesn't know it's producing more power. It doesn't care. It's the exact same amount of input power.
On a production model, what kind of operating noise are you going to have in comparison to what we
Okay,
have
this
here?
is a really crude model. We use plastic in some parts, and you couldn't even do this in a production environment. It should be no more noisy than a spinning generator is initially. Any kind of a generator, not the sound of an internal combustion engine that runs a generator, but just the sound of a generator turning, or any motor turning. Anybody who owns a refrigerator, for instance, has to put up with the noise of the refrigerator as it cycles on, off, and runs. And these are on people's kitchens if you're right in their homes. It'd be no more noisy than that when it's running. Actually be even quieter, because that's also running a compressor. This is the sound of a spinning shaft. This one vibrates a lot because we haven't rebalanced the shaft since we modified it. So it's extremely noisy compared to what a production unit would be. So noise we can get down to be no more noise than anything with a rotating shaft. Like any generator just sort of spins, nothing louder than that. Of course, you couldn't build any housing out of plastic with this one. This is just strictly for a prototype. This one has run for extended periods, it's run for hours without having any problems with it. But for long range production, you'd have to have it all made out of steel, like the original motors are. Like this motor is just completely stock. Normal generator setup, you use one form of induction, having a set of field poles, or in this case we use permanent magnets for simplicity. And you rotate a wire within that field and you produce a certain amount of current. And that's one form of induction they'll refer to as cutting lines of force in most textbooks. There's other forms of induction also, such as these normal transformers work. So you have a AC field that is modulated at, say, 60 hertz or whatever frequency you're using. And that's a secondary form of induction. Or another form of induction would say, textbooks kind of glaze over the differences between the two forms of induction. In a normal generator, they use only one form of induction. They use strictly cutting lines of force induction. And in this generator, we combine two forms of induction. We combine the transform type of induction and the cutting lines of force type of induction. When you do that, you take more advantage of the field that's initially being produced. The real problem with normal generators is that we're not doing anything special with our generator. A normal generator is just not built, designed or built correctly. Most of the magnetic field strength that it creates in order to generate power is wasted. It's just not taken advantage of. All we've done is reclaim some of that magnetic field strength using a secondary form of induction, and that's just one way to do it. There's several different ways to reclaim a lot of the power that's simply not being utilized in a normal generator. A normal generator doesn't have to only put out as much power as it takes in. That's a myth because it was improper design from way back in the 1900s when Nikola Tesla and the original guys were doing their work. Nobody's developed beyond that. Their work was what ended up standing. And in that day and age, putting out more power than it takes in wasn't anybody's concern because power was cheap and plentiful. Nobody really cared. And even when they accomplished that, nobody even talked about it because it just wasn't that big deal. Obviously, things are a lot different in this day and age. And designing a generator that's more efficient, that is to say, puts out more power than it takes in, is a big priority. So that's the basis upon this particular design here. We combine two different forms of induction. Instead of like a normal generator, you have one form of induction. So textbook, they'll tell you that spinning a shaft, like this motor initially would spin a shaft, is what creates electrical power, or the kinetic energy of rotating shafts is converted into electrical power. Well, that's incorrect. Spinning a shaft does not produce any electrical power. It just spins the shaft at the velocity. You put some power into it in a physics kind of way. But you don't actually produce any electrical power. What produces electrical power is the rotating of a wire within a magnetic field, or if you use permanent magnets or electromagnets, they're used in a magnetic field. So rotating the wire within that field is what produces the power. But spinning something, you're not converting kinetic energy to electrical power. That's incorrect. You're converting the energy in the electromagnets and the interaction between the electromagnets and the coil to electrical power. It's a totally different thing. And that's where the error is, as far as seeing where the power comes from. And the power, even in a normal generator, does not come from spinning the shaft. The spinning the shaft is more of a catalytic action. You need to rotate the wire within the magnetic field to cause electricity to flow, to induce the voltage into the wire. But if you spin the shaft with 100 watts of power, or you spin the shaft with 200 watts of power, that's your choice as a designer. How much power you want to put in to create that same amount of power. It just so happens the design is built today that that everybody uses today happens to put out no more power than it takes in because of the particular orientation of the way they design the mechanical design of the motor or the generator unit.